Okay, so good morning. We continue examining the behavior of masonry elements under compression. We looked at a derivation that would allow us to account for geometric second order effects, right. And to begin with, we have examined the effect of the slenderness of the wall and the effect of the eccentricity of the load, represented both as normalized values, h by t for the slenderness and e by t for the eccentricity ratio. So, that is where we were in the last lecture. We looked at a derivation that accounts for the estimate of the vertical load bearing capacity of a masonry wall. URM here is unreinforced masonry. Of course, you will agree that with reinforcement these values will of course change, and we will examine how in a reinforced masonry situation you can estimate capacities of the wall. But currently we are examining the strength of masonry, and now in the component or the element which is the masonry wall itself. So, we made the derivation of the vertical load carrying capacity with a certain set of assumptions which really become the basis of how you get these expressions, how you have these expressions or the curves that you can develop from these. International codes have different bases for developing such force displacement or load deflection curves for compression. They can vary from linear elastic basis to nonlinear stress strain definitions for the material itself. We have examined under linear elastic condition. So, that was our first assumption, that the behavior and compression of the material is linear elastic, and that is why we were able to simplify the distribution of stress to a triangular distribution in the in different sections along the height, right. And that distribution, the triangular distribution, was simplifying the estimates of the cracked length and the uncracked length in each section, which was essential to be able to arrive at an expression for the edge compressive stress Fc. So, this assumption is very important. The second assumption that goes into the calculation of the vertical load bearing capacity is that the material has no tensile strength. Okay. There is some reserve tensile strength. However, we have seen in our previous lectures that this is not something that is uniformly available and dependable, and hence assuming that it is a zero tensile strength material makes sense from an engineering estimate point of view. We also have examined the problem under first order eccentricity, implying that the load eccentricity at the top and the bottom is the same, which may not necessarily be the case if the contact areas at the base of the wall are different from the contact areas at the top of the wall. So, load eccentricity at the top and bottom can be different, but here we have examined the problem under a first order eccentricity where E top is equal to E bottom. We then develop the whole premise that you need a differential equation to examine and solve the elastic buckling problem here, but these differential equations have to be considered differently, because part of the wall where maximum deflections are expected may be cracked, whereas part of the wall could be uncracked. And so, we had different differential equations for the cracked and the uncracked portions, and the classification between cracked and the uncracked portion was on the simple basis that if the total eccentricity lies beyond the middle 1/3 of the cross section, or E by T greater than 1/6, the wall should have cracked, otherwise the wall is uncracked. Again, a further simplification was made. Of course, depending on how much of a section is cracked at different heights of the wall, the curvature will be different, but again that introduces a complexity in terms of arriving at a closed form solution in a simple manner, and therefore we assume that the curvature remains constant along the entire height of the wall itself. This again is a conservative estimate with respect to the exact solution itself. So, what we finally had, if you are examining the estimate of the vertical load at failure, we had P as a function of the edge compressive stress, right. So, as the wall is being loaded from 0 to maximum load at which failure is expected, the edge compressive stress is going to keep increasing. So, we have an estimate of the edge compressive stress, and P, the load, is directly proportional to this edge compressive stress. We have also built in two important aspects that affect the second order effects on the wall, the geometric second order effects on the wall, which are the slenderness ratio H by T and the eccentricity ratio E by T. The calculations have been made for a unit length of wall. In a similar manner, the displacement was also established. In this case, we have assumed a pinned condition for the top and bottom boundaries of the wall, and the force displacement with the displacement at mid height being the maximum displacement is arrived at. So, with the expression you should be able to arrive at a force displacement curve, a P delta curve for the wall itself. So, you start from a 0 load, keep increasing the load, you could estimate it in terms of Fc because you have the edge compressive stress which is directly proportional to P. You keep increasing the edge compressive stress till the edge compressive stress reaches a maximum or you have instability in the system. So, a P delta curve can be obtained for a certain geometry for the load till failure. So, from this single load deflection curve that you estimate, you can identify what is the critical load or P critical as far as the wall is concerned. If you were to work on this problem, you can look at the edge compressive stress incrementally reaching the compressive strength of the material. Fc is the edge compressive stress. Let us say you know the compressive strength of the material, it is the strength of masonry. The wall is not going to be able to fail in crushing because second order effects will govern. So, basically you can increment this ratio Fc by Fm from 0, keep increasing it till a value of 1, meaning that the edge compressive stress has now reached the crushing strength of masonry and you have material failure in the cross section, right. So, as you do this, if before instability is reached the material crushes, then that is the load at which the wall is expected to fail. That becomes your critical value of P or the vertical load bearing capacity of the wall. But in some situations you might not have the crushing strength of the edge compression fiber reaching a value of Fm before the wall fails, due to instability. So, you could either have P critical by Pu reaching a value of 1 before instability, that is the edge compressive stress reaching a compressive strength Fm, or you could have a situation of instability being reached, right. So, the P delta curve that you see here, it has been worked out for two different values of H by T, two different slenderness ratio, and for specific values of compressive strength of the material Fm and modulus of elasticity. These are the values that actually go in, and these curves have been worked out for a single eccentricity ratio E by T, a single value of eccentricity ratio. You can see that you could have a situation with respect to H by T equal to 16, you see that the edge compressive stress reaches a value of the compressive strength of the material, and for all practical purposes you can assume that the wall has reached its failure load, that becomes your P critical. But you might have another situation where the edge compressive stress is still less than the compressive strength of the material, but failure is happening due to instability itself. So, this is what such a set of equations can help you arrive at the load deflection excursion of the entire wall and the P critical, and whether the P critical is occurring due to instability or P critical is occurring due to failure due to crushing of the material itself, right. So, this is what we were targeting. Now, of course, this is mid height displacement and as I told you, we have made these calculations considering a wall that is pinned at the top and the bottom. You could do the same calculations for a wall that is cantilevered, fixed at the bottom and free at the top. You could do the same calculation assuming that the top and the bottom are fixed and not pinned, right. I mentioned that the assumption of the top and the bottom being pinned is a reasonable assumption, because very often you will have cracking at the top and the bottom of a wall occurring due to thermal movements, not because of structural loads. Dissimilar materials are present at the top and the bottom of the wall. Masonry is placed on reinforced concrete, the reinforced concrete slab, or if it is the ground floor you might have the damp proofing course. So, typically due to thermal strains you will have crack formed at the top and the bottom, allowing rotations at the top and the bottom of the wall. So, it is acceptable to assume that the wall is pinned at the top and the bottom, but if you want to assume that it is closer to a fixed situation rather than a pin situation, you have to go back to the boundary conditions that you are imposing in solving the differential equations. Same is true for a wall, let us say a parapet wall, and if you are estimating the load carrying capacity of a parapet wall, I would assume it is fixed at the base and free at the top, and you might want to re-look at the expressions and the boundary conditions used for estimating the expressions, for arriving at the expressions for P and delta. Again, to recall what we have done, we have actually in this case, considering the symmetry of deformations, been working on 1/2 of the height of the wall, right. If you remember, the integration was done from 0 to h by 2 because of the symmetry. So, when you are working on a cantilever, you will have to do it from 0 to h. So, these are some aspects that you might want to keep in mind. One aspect that I touched upon as I was completing the derivation in the previous lecture is that this expression is going to be valid as long as y square is less than or equal to the expression that is under the square root. So, y square minus under root of y square minus fc by 6c into the slenderness, the square of the slenderness ratio. So, the moment y square, the value of fc by 6c into h by t the whole square is greater than y square, you will not have a solution for this expression. Physically, we are looking at instability and the effect of instability in the system. So, you will be able to estimate a peak value, and you will see that beyond the peak value there is going to be a reduction in the load carrying capacity of the wall, but values beyond the limit of y square is equal to fc by 6c into h by t square cannot be estimated. So, that is a limitation that you should be aware of, and as I said, we are interested in the peak value of load that the wall can carry. So, the peak value of load in this case is estimated as the maximum value that you can you see that the wall is able to resist, and typically the limitation that we are talking about would occur a few steps beyond this point, right. So, you need to keep this in mind. So, the curves that you see in the graph here pertain to a single wall, right, or two walls, one wall which has a h by t of 16 and another wall which has a h by t ratio of 18. So, if this is the basis to be able to arrive at the vertical load bearing capacity of a masonry wall of certain dimensions and strengths, compressive strengths of the material, how is that you can look at limits of slenderness ratio, limits of the eccentricity ratio, the load eccentricity ratio on the wall, and that is how typically codes would give you the response of a masonry wall under compression, right. So, what I am trying to examine here is the effect of slenderness ratio, and so I look at several walls with changing eccentricity slenderness ratios and changing eccentricity ratios, and do we get a pattern, and does that pattern give us some indication of how codes are going to be able to give you simple charts for arriving at the load that you must design the wall for and limit eccentricities and slenderness. So, let us examine the effect of slenderness ratio to begin with. The graph that you see here has a number of slenderness ratios. You see that the ratio goes from something as low as 6 to something as high as h by t of 28, okay. And we are reaching practically limiting values when we are talking of a slenderness ratio of 28. So, a slenderness ratio of h by t of 6 is a very thick wall, right, and is not going to be affected so much by second order effects, marginally by second order effects. Primarily if this wall is loaded till failure, it should fail in crushing, it should not fail in buckling. So, this is something that you can see with increasing h by t ratios, the effect of buckling comes into the picture. For initial values that are there in this graph, you are really not looking at any effect, any practical effect of the slenderness itself. The red dotted line that you see there is the value at which, for the strengths considered to prepare this graph, the edge compressive stress actually reaches the value of Fm, which means the curves that you see above beyond the red dotted line really do not make sense, because for all practical purposes the wall cross section has reached its compressive strength, and the curves below that red dotted line is what really matter. Now, one fundamental aspect that we must keep in mind is that these curves have been arrived at assuming we have a triangular distribution of compressive stresses in the compressed zone. We have the entire cross section, part of it is cracked, part of the section is carrying loads and is part of the equilibrium of the system. We are assuming that till failure the stresses there are linear elastic, the triangular distribution continues, but I am sure all of you are familiar with the way we deal with stress distributions at failure in a material like reinforced concrete. There is softening of the material as the material edge compressive stress reaches the compressive strength of the material, because of which the stress distribution cannot be linear. The stress distribution has to take a different shape. Parabolic shape is typically what we start seeing. The edge compressive stress reaches a value of compressive strength and the consecutive fibers start softening. Now, if one were to consider the softening a further level of accuracy in the estimates, these calculations have been based on the linear elastic distribution of stresses in the cross section, implying we have conservatism in this estimate, right. So, if you were to examine different codes in different countries, some of them use a nonlinear stress strain relationship for the cross section, the compressive stress in the cross section. So, if you were to do that, you will get values that are different for same h by t or same e by t ratios. Right. Your question is again to do with what do all these graphs, what do all these curves in this graph represent with respect to the red dotted line that we are looking at, right. Yes, that is exactly what I said, that the red dotted line is the point at which the edge compressive stress reaches the value of compressive strength of the material, okay. So, for all practical purposes, with the for us we are assuming linear elastic response of the cross section. So, we have not built in non-linearity or inelasticity in our estimates. So, we need an artificial way of saying, okay, this is where I stop the response. So, I artificially come and stop the response when the edge compressive stress reaches Fm, which means you are right in saying that the curves above this red dotted line are not to be considered, right. You can estimate them, but you are not to be considering them, simply because crushing would have occurred in the cross section, and that is now dictating the behavior of the wall and not the instability as the equations are going to be prescribing. So, we will examine a close up of the or the lower portion, and it will become clearer to you. But the point that I wanted to make is you can get a deviation from these curves if you use a different code, and that comes specifically because of the fact that this is based on linear elastic distribution of stresses, but in reality you are going to have a nonlinear distribution of stresses. Again, if you were to examine this against real data, you will see that this overestimates, this underestimates the load carrying capacity of the wall, which is erring on the conservative side and good as far as our design approach is concerned. But the reason for the divergence between the real values and these is simply because of the fact that we are assuming an unrealistic distribution of stresses even at failure. That is the point that I want to make. So, if I were to zoom in on the portion of the graph capped by the load at which edge compression stress reaches compressive strength of the material, this is the valid region of the load deflection P delta graph itself for the different walls, and you can immediately see that all those curves depicting walls which have a slenderness ratio that is rather small, which are thick walls, are not governed by instability. You do not see the curve goes way beyond the red dotted line, meaning that they are not governed by instability. The peak values according to those expressions have not been reached yet, but the material crushing has actually occurred, which means those walls are not being governed by second order geometrical effects. Those are being governed by material failure in the cross section itself, whereas the graphs below, the last 1, 2, 3, 4, 5, 6, 7 graphs, which are basically pertaining to H by T ratios of 18 to 28, are the ones which are being governed by second order effects, right. So, I wanted to focus on this to tell you the role H by T plays. It changes the failure mechanism in the wall itself. Now, question would be, okay, what is the maximum H by T that you can consider? And in experimental tests, it has been seen that up to a H by T ratio of 30, right, you can have failure that is limited by the strength, depending on the strength. Again, this set of graphs have been made for a certain compressive strength of the material and a certain modulus of elasticity of the material. If I were to change that, you will have a dependency based on the strength of the material and the stiffness governed by modulus of elasticity of the material. You have a very stiff construction versus a material which is more deformable, you are going to have differences again. So, your assignment will actually make that quite clear to you. But if you look at a practical limit up to which the axial load is limited by strength over buckling, that value is about 30. So, generally speaking, and this statement is general irrespective of strength and stiffness of the wall itself. Now, what it means is if you have a H by T ratio 30 and above, it is so close to instability merely because of its slenderness ratios, you do not need to load the wall, even under its gravity, under its self weight, you can have instability in the wall itself. So, this is if the other aspect that I did not mention, but was there in our initial assumptions, is for our calculations we have not used the self weight of the wall, right, and that is an acceptable assumption, because the self weight of the wall is going to be a very small fraction of the total load carrying capacity, the P critical of the wall itself, and particularly so for smaller values of H by T. So, that is another assumption that comes into the picture, but will not change your estimates significantly. Okay. And it is observed that when you have slender walls, you have significant lateral deflection before it can actually fail. Okay. So, if you were to look at a slender wall and look at the P delta for that wall, you will see, and in fact in this figure you can visually see the lateral deflection that the wall is undergoing, but is still stable, right. So, slender walls show significant lateral deflection before failure, but now the cross section is subjected to quite part of the cross section is cracked, the rest of the cross section is subject to quite a strong gradient in compression, right, strong gradient in compressive strains, and failure will be catastrophic. You get sudden buckling of the cross section because the edge compressive stress has given away, your cross section is already limited because of cracking. So, you can get catastrophic failure. These are tests that have been conducted several years ago, but give us a very clear picture of what sort of a failure mechanism you can get, and that is fundamentally the reason why slenderness ratios are limited by codes, that you have cap on the slenderness ratios, because what you get by optimizing is a very brittle failure mechanism. That is, and codes typically tend to avoid occurrence of brittle failure mechanisms. You want to avoid the occurrence of brittle failure mechanisms, and you will start appreciating in a few lectures that depending on the earthquake zone that we are working in, the slenderness ratios of walls is further limited. So, if you are in a high earthquake zone, slenderness ratios can come down to as low as 12, and that is simply because you have lateral forces along with the gravity forces. Under gravity forces, to avoid buckling controlled behavior, you limit the slenderness ratios, but in the presence of lateral forces you have, if you have very slender walls, you have out of plane failure which cannot be controlled, and so you have slenderness ratios which are controlled to prevent premature out of plane failure. That is not primarily in compression, but because of the lateral forces. But we come back to the concept of slenderness ratios being controlled. In this case it is being controlled for gravity, but in earthquake zones it is controlled to avoid significant lateral deflection and failure due to the inertial forces themselves. So, that is a point that we will come back to very soon. Okay. So, I wanted to show you how with this sort of an estimate code would then structural code would then give you the framework within which you design walls under second order effects. So, as I was mentioning earlier, I can take a single wall for a given strength of the masonry and modulus of elasticity. You remember that modulus of elasticity, we could have an empirical relationship between the modulus of elasticity and the compressive strength. So, Em, the modulus of elasticity of the material, could be K times Fm. So, Fm known, I have the modulus of elasticity with me, and so for a single wall I keep incrementing the edge compressive stress and I get the P critical. Now, I can look at different walls and be able to arrive at, with respect to slenderness ratio and with respect to E by T, what sort of trends can I get, and that is what codes typically give you in terms of graphs. So, if you look at the effect of eccentricity ratio now, this graph here is making use of, I would say, several walls where the eccentricity ratio is varying from no eccentricity of the axial load, which is concentric compression, to a very high eccentricity ratio of E by T of 0.4, right. And if you remember, we said if you have an E by T of 1 by 6, right, plus or minus 1 by 6, that is the middle third, you can start having cracking in the wall, but codes would typically allow you to go up to about 1/3 or even 1/2. 1/2 is typically when you will start having instability. So, you can see that here here these graphs that have been made, these curves that have been made are for 5 different values of eccentricity ratio, E by T going from 0 all the way to E by T of 0.4. Now, I use walls of different H by T. So, if you can see the x axis here, in the x axis we have different H by T ratios going all the way from 0 to 50, which means I am basically looking at different geometrical configurations of height and the cross sectional dimension T of the wall. So, I have an entire range from 0 to 50, and in those walls I am changing the eccentricity ratio from 0, no eccentricity of load, to an eccentricity of 0.4 by T. I will be able to estimate the P critical for each wall, right. I have an entire matrix now, different values of H by T, different values of E by T, and for each of those I estimate what is the P critical. Some of them will fail by instability being reached, some of them will fail by the crushing of the cross section, but I have now the entire set of values of P critical, and if I normalize P critical by Pu, Pu being nothing but the compressive strength of the cross section, right, the load at which compressive strength of the cross section is reached. So, Pu is nothing but Fm into thickness of the wall into length of the wall, right. If I do that, then this is the kind of effect that you would see with increasing eccentricity ratios. You see that there is a drastic drop in the critical load at which failure due to compression is happening with respect to the material strength defined by Pu, right. So, this is one graph where you are looking at both the effect of the eccentricity ratio and the effect of the slenderness ratio, and you will appreciate that the effect of the eccentricity ratio is quite drastic. You see, when you have no eccentricity, the black line at the top, to with moderately increasing eccentricity ratios, you get a drastic reduction in the load carrying capacity of the wall in compression. You are reaching values of 10% of the compressive strength of the material. So, the second order effects have a very significant role and have to be accounted for in estimating the value of the vertical load carrying capacity of the wall itself. So, I have here a graph that looks at how our code, the IS code, presents the reduction factors. So, what you saw in the previous slide was really the reduction factor that you must consider if you have a certain eccentricity ratio of loading E by T or a certain H by T ratio, the slenderness of the wall itself. So, these are limiting curves, but mind you, these curves are again from the equations that we have developed based on linear elastic distribution of stresses in the cross section. So, with the example of IS 1905, 1987, which is a code based on permissible stresses, the way the design occurs as far as 1905 is by limiting the stresses that will occur in the masonry for compression due to gravity forces or compression due to gravity forces plus lateral forces. So, you have to arrive at what is the permissible level of compressive stress. To be able to arrive at the permissible level of compressive stress, what the code requires is that the estimate of what is referred to as a basic compressive stress, and we will examine this concept in future classes as well. The basic compressive stress, which is nothing but the compressive strength of the material, denoted as Fb, is then multiplied by a factor that accounts for the slenderness ratio and the eccentricity ratio together, right. So, what the code does is it requires that the eccentricity H by T, slenderness H by T and the eccentricity E by T together gives you a factor that you can use as a stress reduction factor. This stress reduction factor is in IS code referred to as Ks. You multiply this with the basic compressive stress Fb. Okay. Now, this is then multiplied with other factors which we will examine subsequently, but the point is the basic compressive stress is a factored strength of the material. For example, if I know that the strength of the masonry is 4 MPa at failure, this being a code that deals with working stresses will not take the value of 4 MPa, will probably use a factor of safety of 4 and say that the basic compressive stress, which is your limiting compressive stress under working loads, is 4 MPa by 4.1 MPa. So, 1 MPa would be the basic compressive stress, which is your limiting compressive stress. That limiting compressive stress is further reduced by what is referred to as a stress reduction factor, and this value of the stress reduction factor is something that you can arrive at based on the eccentricity ratio of the load and the h by t ratio. So, if you look at this graph here, this is the graphical representation of a table number 9, which is given in the IS code, IS 1905, which will tell you, okay, I know the total eccentricity ratio of the loads coming onto the wall, I know the slenderness that I am going to be adopting, what is the Ks factor that I must further reduce the working stress, the basic compressive stress Fb by to account for second order effects. And you can again see here that if I am looking at a wall of 6, h by t of 6, that is where we start, you have a h by t of equal to 6, you have 0, I mean your correction factor is 1, there is no correction required for a wall which has a slenderness ratio of h by t 6. So, that is where the calculation starts from, and you see that we reach values of 27. In the code we go up to value of 27, that is the value here, and you see that the stress reduction factors are of the order of 0.2 and slightly more than 0.2, which means the permissible stress is going to be reduced so much. Already you have reduced the permissible stresses to account for the working stresses, and then you further reduce it to account for the second order effects. So, Fb in reality, and we will come back and examine this later, Fb is multiplied by 3 factors. A stress reduction factor is what we talked about, there is an area reduction factor and a shape reduction factor which come in later. For the time being, you can assume that both are 1, then the only factor that you multiply Fb with is Ks, and the Ks is what you get from this graph itself, right, correct. So, the you have to make an estimate of the eccentricity, have an estimate of the eccentricity of the load, and that allows you to estimate the eccentricity ratio E by T. So, you know E by T, you have chosen a certain H by T for the wall construction, and then you look at what the stress reduction factor is. Now, if the stress reduction factor into the basic compressive stress for the chosen material, let us say you have chosen a material which is of a compressive strength 8 megapascals or 8 Newton per millimeter square, the Fb would be about 1/4 of that value. So, I have 2 MPa of basic compressive stress into a stress reduction factor. Now, let us say you arrive at the permissible stress by multiplying Ks into Fb, but it is far lower than what you want as the load carrying capacity of the wall. Your only options are change the wall cross section or change the material by increasing the strength of the material. So, it gives you a framework within which you can look at dimensioning your masonry walls or choosing the strength of the masonry wall itself, right. That is as far as unreinforced masonry design is concerned, and the use of these factors to account for stress reduction itself. Okay. So, I think I will stop here and look at the rest of the international codes and how this is adopted, and also the effect of other geometrical effects like wall slab interaction and the rotation of the joint, how it is going to affect your assumptions on the boundary conditions of the wall and whether that is going to affect the compressive strength or the load carrying capacity of the wall. See you in the next lecture.